Alright, so we are continuing with our study of delay differential equations, and with the simplest one, which is x dot at t equals minus ax at t minus 1. You will note that if I say tau equals beta t, then dx dt equals beta dx d tau. Now at t and at tau, right? So this is because t equals tau by beta. Okay. Now a delay of 1 in t is a delay of beta in tau, and so we will have beta dx tau d tau is equal to minus ax at tau minus beta. This one will go here. This delay will change from 1 to beta, and so the delay is not special. The one is just for convenience. Alright, so let us return to this equation here, and we have the characteristic equation, which is lambda equal plus a e to the minus lambda equals 0. I mentioned in the previous lecture that for small, we will assume a is greater than 0. For small a, we have 1 lambda is approximately minus a. Okay, so that's one thing we noted. Another is that there are infinitely many roots, large negative real parts. Okay, all right. So let's look at some of these roots, and a good way to do it is to find the gradient here. So remember Newton-Raphson. Okay, let's just implement it in the complex world, it doesn't matter. So f of lambda equals 0 is what we are trying to solve. That's f of lambda there. F prime of lambda equals 1 minus a e to the minus lambda, and then we will have lambda k plus 1. This is the iteration. Lambda k plus 1, not the k plus 1th root, the k plus 1th iterate, is equal to lambda k minus f of lambda k by f prime of lambda k. This is the Newton-Raphson iteration, and we can do this in MATLAB. So let's turn to MATLAB here, and we will look at this part later, but I have to choose an a. So let me choose a fairly arbitrary a here, clear all, and then say that's a. Okay, now let me say x is equal to random 301. So this is a number that goes between 0 and 1. So let me multiply it by 30. So now it goes from 0 to 30. Let me subtract 20, and so now it goes from minus 20 to plus 10. Okay, I have 300 such points. Let me say y is equal to rand 301 times 40. So now y goes from 0 to 40. This is because our roots are complex conjugates. So if x plus iy is a root, x minus iy is also a root, and we don't have to find both of them necessarily. So I can show you my guesses and my initial guesses, and the initial guesses are like this. They're sort of scattered all over the place. You can see the points. Okay, very good. Now what I will do is I will say z is equal to x plus I times y, and then what I will do is I will say for k equals 1 to 100, f equals z plus a times exp minus z. Now that's a complex number, but I don't care. And then I will say fp is equal to 1 minus a times exp minus z. So that's f prime. And then I will say z is equal to z minus f by fp. That's the Newton iteration. And I've done 100 Newton iterations, okay, for each of those 300 points. Very good. Then what I will do is I will say I have the final f values. The second last one is just as good, right? So even before the iterate, it's all right. And so what I will do is I will say mn is equal to sort abs f. Okay. Why am I doing that? If you look at the m's, you will see why. Let's see, I'll just hit it here. And you will see there are a bunch of them that are a bit big, and then many look like 0. And basically every single one has converged. Right? Every single one, every single initial guess has converged to some root. So that's very good. That means we can just use those roots. So let us then go to plot real part of z, imaginary part of z with a circle, and these are the roots. Okay. So you can see that there is a pattern over here. We have a pair of roots over there somewhere. We may have missed a real root. I'm not sure. This one is the complex conjugate possibly of that one. And we may have missed a couple of roots here. So this numerical method has some issues, but it's giving us these roots. Okay, so what we can do now is we have these roots to check our results against. Okay, is there a positive root? We will see. Okay, there may not be one, but it might be a better idea to do the following. So how about instead of 300, I take 3000. Okay, and how about I make this 40, and then I have some larger values there, and then I have y equals, and I make that 3000, that's good enough. And then I have z equals that, and then I go, instead of 100, I go to 1000 iterations. And I've done that, and then I say mn. Okay, so I've sorted them. Now let me plot m. And this time you see some of them have not converged. They've gone up to 10 to the 110 right over here. If I plot it with dots, you will see it comes all the way here, but are they all 0? I don't know. So what I will do is I will say sum of absolute value of m less than 1e minus 8. Okay, and what I have found is that 2990 of these roots have converged. And so what I will do is I have sorted them with m and n here. So I will say z is equal to z of n. Those are the roots, and then I will say z equals z 1 to 2990. Now these are my converged roots. And now if I use this plot command, so I've got some very large root over there, but that's not important. This is the important part here. Let me try grid. Try grid here, and let's look here, and you will see that there are these roots here which we have to figure out. We may have missed some roots over there, but over here we are not getting anything else. Okay, there are ways of checking these roots and so on, but let us try to understand this distribution of roots. So one way to do that is to go back to our analytical treatment and think of whether there are any positive roots. So to have a root in the right half plane, the root must cross. So here is some root which goes over. This is the as a changes, right? So as a increases from 0, maybe some roots cross over, cross over. Okay, so let that one be plus minus I omega, so we can take omega greater than equal to 0, and we are also looking for a special value of a. This is a very common trick. So our equation was then lambda plus a e to the power minus lambda equals 0. We will put lambda equals I omega. We will get I omega plus a cos omega, let me see now, minus I sine omega equals 0, and then this will be separated into real part and imaginary part. For ease of visibility, I will write it here. So we will have a cos omega equals 0. That is the real part. This means sine of omega is plus 1 or minus 1. See, because a is not 0, a is greater than 0, therefore cos omega is 0. The other equation is omega equals a sine omega. We have assumed a is positive, omega is positive. Sine omega is plus or minus 1 according to this equation. According to this equation, we know that it is plus 1 only. Okay, good. So if sine omega is plus 1, that means omega is equal to 2n plus half pi, which means a is equal to 2n plus half pi, and which means that the smallest value of a for which a pair of roots or any root can cross over to the right hand side is pi by 2. That is the smallest one, and when that happens, omega is pi by 2. Clear so far? Very good. Let's look at large roots. So as we have noted here, there are some large roots. These roots have large negative real parts. It may seem like a small thing on the graph. Look at the scale. Okay, so in the scale, what is happening is this root is quite large. It is 100. This root is quite large. It is 20, and this real part is smaller, but we'll sort of figure that out. Okay, we'll see how that goes. So let's move here to the left side and let's think of large roots. So now a is arbitrary. We seek large roots. Okay, all right. So we have, let us say, lambda plus a e to the minus lambda equals 0. Let lambda be equal to p plus I q. Q is greater than 0, and we expect p to be less than 0, and we expect q to be big. Okay, so here I have p plus I q plus a e to the minus p cos q minus I sine q equals 0. Okay, that's what I have. collecting real and imaginary parts, I have p plus a e to the minus p cos q equals 0, and I have q is equal to a e to the minus p sine q. Okay. In the analysis we just did earlier, where we were looking for a special a, p was 0. Now p is not 0, but what we have is q is big and possibly p is big. Their relative bigness we have to sort out, but let's continue and see how that goes. All right. So we come here and we realize that we have a problem, right? What is the problem? The problem is that if p is very big, in that case, for this to work, p has to be negative. But if p is, because if p is positive, then this is exponentially small. If p is positive and big, then this is exponentially small, and it cannot hold at all. So that means p is less than 0 and big, and we are considering this equation now, just the real part. Okay, right. So then we have, if p is less than 0 and big, then we have e to the minus p is much bigger than p. Okay, and then the only way that will work is that cos q has to be tiny. That means sine q is basically 1. So we come to the next equation. Okay, by assumption q is positive, a is positive, e to the minus p has to be positive, sine q is basically 1. So what is q? Once again, just as we have seen, this means q is equal to 2n plus half pi. Okay, very good. So if q is 2n plus half pi, sine q is 1. This is an approximate solution now, but holds for large n. Okay, so if q is 2n plus half pi, whatever that q is, we've put it in there, so that is, let's say, qn. Okay, so qn is 2n plus half pi. This is the nth approximation. Okay, so then I have, let me use red here for easier visibility, qn by a equals e to the power minus pn. Okay, and so pn is equal to minus log qn by a. That's the answer. Okay, so now let's come back to MATLAB, and here are my guesses now. So I will say n equals 1 to 10. Okay, all right, qn equals 2 times n plus half times pi. Pn equals minus log qn by a. All right, very good. Let me hold on, remind you that I have this graph here. Okay, and now let me insert red pluses over here. So I'll say plot pn qn red pluses. Okay, and now if we zoom in here, you will see there is very little doubt that our approximations are very good. This one over here was a missing root. Numerically, we did not find it from our grid search. The ones that we found, the match is extremely good. The very first one, we did not put n equals 0 and we have not compared. It is not supposed to work there, but for large n it works very well. We can even put n equals 0 and see. So let us say n equals, and then let me say 0 to 10. Of course, you know, if it doesn't work, we can't complain, but that's Qn, that's Pn, and we can just make the plot again. And you see, even this route is not really that bad, right? But it's, you know, could be better. But okay, so those are the routes that we have. Okay, now what happens when I have a equals pi by 2? When I have a equals pi by 2, these roots go over to the imaginary axis. Okay, so that is when we will have beyond a equals pi by 2, we will have growing solutions. So according to our analysis, it now seems that the system is stable because a needs to be at least pi by 2 and it's not yet pi by 2. All solutions are decaying. Now we have to go to DDE 23 to solve that, and we will do that later, but I will just show you how DDE 23 works. Let me do that this way. So the simplest way to use DDE 23, is, let's see, you can define your error options. That's important. So you have the function DDE fun, you have to give it the lags in a series, you have to give it a function that gives you the history, that is the initial function, okay, and tspan. So we might as well do it. So over here, let me open, let's see, I have to start a new file. So let me start a new file here, and let me say function x dot equals DDE example. Now let's go back here and see what our function has to return. Oh, that's not what here. What our function has to return. DDE fun is a function handle. It will be given t, y, and z is a column vector corresponding to the delays. So over here I will say t, x, z, okay, and then I will say a equals whatever 1.2 something, some number, and then I will say x dot equals minus a times z, because I have only one delay. This is my differential equation. Okay, so this is DDE example. I will need another function which will be function zz is equal to DDE history of t. Why history of t? We have to see this history part. Okay, so let's see now. History can be a function handle where for a scalar t it returns a column vector. So that's all it is. So we will take DD history. Now what we will do is, we know that it is a scalar, actually our case. We can try 1. So it is a scalar, uniform input. Okay, so we can say zz equals 1. Just for the moment, we can try that. Okay, so let us try that. DDE history. Lags. So we have lags. Lags have to be defined here. I'll call it LL equals 1. So those are the lags. I'll say OP equals ODE set and DDE set and so on. So I have that now. And then when I come in here, what else do I need? Function, lags, history, tspan and options. Okay, so now I need tspan. So I'll say TSP equals linspace 0, 30, 400. Let's try that. Okay, and then this does not give T and X, it gives a funny structure. It gives this solution structure, right? So DDE23, function name, lags, history. Okay, so here we go like this. We say sol DDE equals DDE23. Then I have to give it the name of the function. The name of the function is DDEEX. Then I have to give it the lags, for which my name is LL. Then I have to give it the history, which is DDE history. Then I have to give it the tspan. Then I have to give it the options. Okay, and after I've done that, to plot it, I have to do something else. I have to sol.x and sol.y. So I'll say here T equals sol DDE dot x and x equals sol DDE dot y, and finally I have my solution CLF. Finally I have my solution plot Tx, and that's the solution to the delay differential equation. Okay, so it is showing some exponentials. I would like you to pay close attention to this early part. That is because the initial value was given as 1. Because the initial value was given as 1, for up to 1, x dot was just minus a and the delayed value, you see. All right. What is this root here? This oscillation, this is the slowest decaying oscillation. Okay. But now we can give it other initial conditions and then we will see how it goes. So one way to do that is I still have, let's see now, plot Z, no, plot VL pattern. So I have these solutions with me here, and so you see this is the slowest part, right? So this is the part that I have there, and how much is it? It's about minus 1 point, right? So this is basically let's see, what I needed is minus 0.1464. That's what I needed. So let me plot T, X, T and e to the power minus 0.1464 times t, just to see whether the exponential rate is the same, and you will see that it is basically the same. This match is some kind of accident. It's, it's not supposed to be exactly that, but you will see that this is the slowest decaying exponential. Is that all right? Now let us do something else. I want you to understand that initial conditions are really important, and so let's come here and look at not this route but this route. Now this is a much faster decaying route, right? And this route we have a really good estimate for it, but we will read off the number and it will be better. So here what we will do is I will say Tt equals G input. I can get it from Z, but that's okay. I'll just get it from here. Okay. So let's see. Okay, very good. So here is what I will do. See, this is a faster decaying solution, right? Suppose my initial condition is in that direction. In that case, when I solve, you see it won't match. It won't match the old exponential rate. You see the old exponential rate is here. It has decayed according to this rate, which is a much different rate. What is this rate? It is this rate here, minus 1 point, right? So if I come here and I put that rate, then I should get a better match, as indeed I do, right? So you can see that the solution to the delay differential equation has within it the possibility. This match is some kind of coincidence, okay, this near match, but you can see that the exponential decay rate is just perfectly correct, okay. So let's recapitulate. We have a delay differential equation. This is a very simple example. It's linear constant coefficient. It leads to a characteristic equation, which is a transcendental equation. It has infinitely many roots. We have some assumed limits, constraints on the parameters. We may be able to say something for when the parameters are small, but we are really interested in the parameters not being that small, the delay being not small, and so on. And then when we look at that, we can look at roots using Newton-Raphson and get some kind of grid point and find several roots. But we can also look at bifurcation points. Then we are interested in special values of the parameter and we assume pure imaginary roots. In this case, we are able to get a satisfactory solution, and we know that pi by 2 is the special value at which bifurcation occurs, and beyond that exponential growth occurs. And then we can also get fairly, with a bit of cleverness and thinking, we are able to get fairly good approximations for large roots. So this discussion will close once we come here, and instead of this I say pi by 2 plus 0.1, and now I will get expansion, you see, and then I can come to history and just make it arbitrary. It doesn't matter. Let me say t. It doesn't matter, you know, some initial condition, and then I say solve. There you go. And then we will say t equals and x equals, and this time we expect a growing solution, okay. So here, this exponential has no business being there. It is no longer relevant. We have changed a, but you see now there is a growing solution, right? Since this is past pi by 2, a is not small, right? A is a little bit bigger than pi by 2, right? If a was exactly pi by 2, we would have a solution that was perfectly sinusoidal, okay. All right, this system still has hidden in it decaying solutions corresponding to the other roots that are still in the left half plane, and if you choose your history to match one of those, then at least for some time you will see that same exponential decay. The exact solution happens to be that, but due to arithmetic errors, tiny round of errors and so on, eventually the instability will set in, and eventually you will have growth at this rate. Since pi by 2 is the bifurcation value, and since we have barely crossed it, so we have not crossed the others, there is only one pair of roots in the right half plane, and this is the only growing exponential solution that you will see. We will stop here with this lecture. Thank you.